Let's take a look at the next example. In example 3, we want to write the sum from n equals 2 to infinity of n times n minus 1 c to the n x to the n minus 2 minus the sum from n equals 0 to infinity of cn x to the n plus 1 as one power series. Okay. And right now, if we kind of look and try to see what's happening here, if we were to plug n equals to 2 into this first expression, we would get some coefficient, but then we would have x to the 2 minus 2, which is x to the 0, which would be our constant term. So the first term in this series, because of the index and the power of x, starts with a constant term. However, if we come over here and we plug n equals to 0 into this power series, then what we would see is that this term would start with x plus 1, which would be x to the first. One of the things that we're going to need to do in order to add these power series is we want each power series to start at the same power of x. So here's the way we can accomplish this. What we're going to do is let's write out the first term here in this series. So if we plug in n equals to 2, we get 2 times 2 minus 1. This would be c to the second. And then we just saw this is x to the 0, which is 1. So we get this constant. Plus, then we would have the remainder of the sum. And that would then be the sum from n equals 3 to infinity of n times n minus 1, c to the n, x to the n minus 2. And now in this regards, they both start at exactly the same exponent. Okay? But the one thing that's going to be different is that this index starts at 3 and this index starts at 0. So one of the things we can do is we can do a substitution on this. Again, the actual variable itself, n, is just a dummy variable. Doesn't matter whether you call it n, st, or whatever. But let's, in the first sum, we'll call it k. Let's let k be this exponent, which is going to be n minus 2. And again, it's just a dummy variable. So it doesn't matter really, it's not the same k necessarily. But in this series, let's call it k equals to n plus 1, which would again be the exponent of this thing. We know that they're both going to start at the same power now because we broke off that first term. And so ultimately, after we do the substitution, we should be able to kind of go ahead and combine things. So if we let k be equals to n minus 2, we can also solve this equation for n, and this would mean that k plus 2 equals to n. Similarly here, we can subtract 1 from both sides, and we see that k minus 1 is equal to n. With this substitution, we can write our sum as follows. This is going to be 2 minus 1, which is 1. So we simply get a 2c2 plus the sum. And now, again, we're switching from the variable n to the variable k for our index of summation. Notice that this one started when n equals to 3. When n equals to 3, then k is going to be 3 minus 2, which is 1. So the index of summation will start at 1. And of course, if n is going from 3 to infinity, when n gets large, k gets large. So k will be going from now 1 to infinity. Everywhere we see an n, we can replace it with the expression for k. We know that n is k plus 2. So this is going to be k plus 2 times, plugging in k plus 2 here, we get k plus 2 minus 1, c to the k plus 2, and now again our choice of substitution, this is now going to simply be x to the k. Similarly over here, we're going to get the sum from k equals, the original index of summation n started at 0. If n starts at 0, then k is going to start at 0 plus 1, which is 1. So this is going to be the sum from k equals 1. Obviously, if n goes towards infinity, then k will also go towards infinity under the substitution. We get c to the n, which is k minus 1, and then it's going to be x to the, this was our defined k. And now one of the things we notice is that the index is the same. They both start at 1, but also, and perhaps more importantly, is that they're both going to start with that first power term of x. So we will be able to write this as one series. So this is equal to 2c2 times the sum from k equals 1 to infinity. And I'm just going to write, so both of these have k's. We're just going to, factor out the x to the k and subtract the coefficients. This factor is k plus 2 times k, this is going to be a plus 1, times c to the k plus 2. And then we're subtracting this coefficient, which is c to the k minus 1. And now we've taken this, the difference of these two sums, and we were able to write it as a single power series. Oops, sorry. Should be a plus sign in between, right? This plus sign came from right there. By, first of all, breaking off terms as necessary. So you might need to write out the first few terms of one series or another just to make sure that they end up starting at the same power of x. Once we do that, we can re-index using a dummy variable. I will typically always use k in the notes. And then once you kind of have them starting at the same power of x with the same dummy variable, then we can go ahead and combine the terms to form one power series. So what we're going to look at next is a way to solve differential equations using power series. And this is a pretty powerful technique. Okay, let's find a power series solution. So let's suppose that we have a solution of the form y equals the sum from n equals 0 to infinity of cn x to the n of the differential equation y prime plus y equals to 0. This equation, by the way, is one we've solved a lot in the class. We would know from our previous methods, we already know the solution to this. So we know that the solution is simply going to be, e to the negative t. Okay, or perhaps that should be e to the negative x, that is. So constant times e to the negative x. We know that's going to be the solution. But that's not kind of the point of this one. We will encounter several types of differential equations later that we don't know how to solve. And oftentimes, if we can't find the solution explicitly via one of our analytical methods, we can try to assume that we have a solution with its power series, and then maybe see if we can solve for the power series of a function that would be a solution to this one. Okay. So, as we've seen before, what we need to do is we need to take this, and we need to plug it into this differential equation, which means we first need to begin by computing y prime. So y prime of this power series is equal to, we differentiate term by term, remembering that every time you differentiate, you start the index up 1, because the first term in this series, if you look at the 0th term, the 0th term would be simply c0 x to the 0, which is just a constant. And we know that the derivative of any constant is 0, and so we don't need to add 0 separately. We can drop that term, and thus it's going to start now from n equals 2 to 1. We bring the power down, n times c to the n, and now reduce the power of n by 1, so x to the n minus 1. We're going to plug these power series into our differential equation. So it's y prime, which is the sum from n equals infinity to n, cn x to the n minus 1, plus y, which is the sum from n equals 0 to infinity of cn x to the n, and this is supposed to be equal to 0. We would like to, it's going to be helpful, let's combine the power series on the left-hand side into a single series, keeping in mind that this one here, when n equals to 1, if we plug 1 in, that would give us x to the 0, which is 1. So this power series is going to start with a constant term. Similarly, if we plug 0 into this one, we would get x to the 0 with a coefficient, which is also going to be a constant of 1. So already, both of these power series start with a constant. So we can go right ahead and try to do a substitution of the index. Let's re-index these, and let x be the exponent of each expression. So let's let, in the first power series, let's let k be n minus 1, and then naturally k plus 1 would be equal to n. And then over here, not much of a change at all, just let k be equal to n. Yeah, k is just going to be n. So, under this re-indexing, here's what we get. This is going to be the sum. Now from k equals. Now this series started when n equals to 1. When n is 1, k is going to be 0. So it's going to be from k equals to 0 to infinity of n times cn. That's going to be k plus 1 times ck x to the k plus the sum from k equals 0 to infinity. This is simply going to be ck x to the k equals to 0. Now that we have these starting at the same power of x and the same index, we can go ahead and combine them. This is the sum from k equals 0 to infinity. And I'll factor out the x to the k term. And then when we add those coefficients together, we simply get k plus 1 ck plus ck. Oops, sorry, something's not right here. Didn't do this substitution right there. So we said k, everywhere we see an n in the first expression, we should be putting k plus 1. This is going to be k plus 1, ck plus 1. So this should be plus 1 there. And now we're almost ready to kind of go ahead and solve this thing, where one of the things that we notice is that we have a power series on this left-hand side, and this power series is equal to 0. Well, that implies that all of these coefficients are going to have to be equal to 0. And you can kind of think of it as like an equality of the terms of the power series. Here on the right-hand side is just equal to 0. So you could think of that as a power series where every coefficient of the x term would be 0. Therefore, these coefficients are equal to 0. So let's take this and set it equal to 0. And what this is going to provide is a recursive relationship for our variables that involve ck. Typically what you would want to do is always solve it for the one that has the largest index. So let's take this equation and let's solve it for ck plus 1. You would begin by subtracting ck from both sides, then simply divide by k plus 1, and what we get is the following. ck plus 1 is equal to negative 1 divided by k plus 1 times ck. And this recursive relationship is valid for k equals 0 through infinity. So now what we're going to do is let's actually go ahead and compute a few of these values for ck. So if we plug n equals to 0 into this recursive relation, this is what we would find. So we know that ck plus 1 is equal to negative 1 over k plus 1 ck. When k equals to 0, then this is going to be c of 0 plus 1, which is 1, is equal to negative 1 divided by 0 plus 1 c0, which is simply equal to the negative of c0. So we get that c1 equals negative c0. Okay. Let's go ahead now and plug in k equals to 1. When k equals to 1, this is going to give us c of 1 plus 1, which is c2. This is going to be equal to negative 1 divided by 1 plus 1 c1, which is equal to negative 1 half c1. But from just a moment ago, we know what c1 is equal to. c1 is equal to the negative of c0, which is going to be positive 1 half c0. Let's do a few more of these. When k is equal to 2, we plug a 2 into this formula. We would get that c3 is equal to negative 1 divided by 2 plus 1 c2, which is negative 1/3 c2. But again, we know what c2 is equal to from here. We saw that c2 is equal to 1 half of c0. So this gives us negative 1/6 c0, and we quickly kind of realize that this pattern is going to continue. So essentially what's happening here is, all of these coefficients are going to be expressed in terms of the first one, which was c0. If we do k equals to 3, then we would find that c4 would be equal to, plug it in, this is going to be a negative 1/4 c3, which is negative 1/4 times negative 1/6 c0, and that would be equal to a 1/24, positive 1/24. And then we can kind of continue on with this, but let's kind of take a look in a moment and see what's going on here. So we have, again, our original solution, so our y equals our power series here. It's going to be the first term, our constant term, which we know is c0. Then we have a minus c0x plus a 1 half c0. That would be our x squared term. Just kind of keep writing it out. Then we have our minus 1/6 c0x cubed. We have our plus 1/24 c0x to the fourth. Okay, and so that's our solution. We were actually able to kind of find it in our power series. And by just kind of looking at the pattern, we can write this power series in closed form notation very easily. This is y equals, it's the sum from n equals 0 to infinity. Every coefficient is c0, but then notice what's happening here. We have an alternating negative 1 sign. We have x to the n. And then in addition to that, if you keep track of the numbers that are kind of at the bottom here, these, hopefully you recognize these as like factorials. So this is like 0 factorial, which is 1. 1 factorial is also 1. 2 factorial is 2. This would be 3 factorial, which is 3. So essentially all of those denominators are really of the form n factorial. Of course, if we wanted to, we could pull out the c0. So that's our answer in power series form. But to reconcile this against what we know is the solution in the very beginning, we can rewrite this as c0, pull the c0 out. These are both to the nth power, so we can think of this as negative x to the n, all divided by n factorial. And if I just kind of maybe delete the negative x to the n for a moment, so it's a negative x in there. This thing here, we recognize that as being the power series for e to the x. But with a negative x plugged in, this is simply c0 e to the negative x, which is what we knew the solution was up front, because we knew how to solve homogeneous linear differential equations for a while. So This would be a very powerful method for us, a very nice analytical technique to finding solutions, if you can't otherwise, is to assume that this series has a power series solution. We then go ahead and differentiate as needed. We plug those power series into the differential equation. We break off terms and re-index so that we can combine them into a single series, and then we equate coefficients to write out the power series solution for our solution.